Okay, so today's lecture is just for fun. Maybe that's why the attendance is sparse. So I said that I'd show you how Green's theorem is used, can be used to get a fundamental result in complex analysis. Okay. So sort of like a crash course in complex analysis, leading up to so-called a quick introduction to something called Cauchy's theorem.
So skipping analysis and going straight to complex analysis?
Yeah.
Nice.
Yeah. So we've got Green's theorem already. We've got Green's theorem already. Let's show how you can use it to get one of the really most fundamental results of complex analysis. If you take a course in complex analysis, you'll find that everything is based on something called Cauchy's integral formula. Cauchy's integral formula, in turn, is based on something called Cauchy's theorem or Cauchy-Riemann. Cauchy is the first person who proved it. I mean, Riemann showed that you didn't need as many conditions on it as Cauchy had put. Okay, so in any case, so sort of a crash course in complex analysis, getting up to the use of Green's theorem and Cauchy's theorem. Okay, so just some. Okay, so here is. So here is the real line. Here's the real line, and here is the imaginary numbers. Okay. So these two together give you the complex plane, right? So this is the number 1, this is the number I, right? This point here is 1 plus I, right? Okay. So you've got the complex. This is the so-called complex plane. Okay. If you have some point here, a plus bi, right? A plus bi, and this is your a, right? This is your b, right? And so obviously, and one uses usually z as your variable in complex numbers. Either z or zeta are used as your variables. So we call A the real part of Z, right? The real part of Z, sort of obvious definitions. We call B the imaginary part of Z. Okay. What you would expect. Okay. Real part of Z, imaginary part of Z. Okay. Okay. Right. So you have some guy Z here, A plus bi. Another thing that another useful concept is something called the complex conjugate. So this is called the complex conjugate. It is defined as A minus bi. A minus bi. It's, as you see, it's the reflection of the number across the real axis. Okay, that guy's called the complex conjugate. Okay. So we'll sometimes write it A plus bi. We'll also sometimes write it just A comma b. Okay. If you see me writing A comma b, what I mean is A plus bi. Okay. Some simple observations. First, what happens if I take Z plus its complex conjugate? If I take Z and I add on to it its complex conjugate, what happens? Well, the imaginary parts will cancel off, and you end up with twice A, right? You end up with twice A, so you get twice the real part. Right? Z z plus its complex conjugate is twice the real part. Or you could say, the real part is z plus its complex conjugate divided by 2, if you felt like it. Right? Real part of z is z plus the complex conjugate divided by 2. Right? If I take z minus the complex conjugate, what do I get? You get 2 times, well, the real parts will cancel off, right? You get bi minus bi, so you get 2bi, right? So you get 2I times the imaginary part of z. Right? Right. Or in other words, the imaginary part of z is the same thing as z minus z bar divided by 2i. Other things that come in handy, if you take the product of complex conjugates, it's the same thing as if you take the product and then take the complex conjugate of the product, right? So if you have these two numbers, z and w, and you reflect them and multiply them, it's the same thing as if you multiply them and then reflect them. Okay, so that requires a little bit of calculation, but it's pretty straightforward, right? I mean, you would just multiply a minus bi, c minus di, and see that equals the product conjugated. Okay. Another thing that we probably won't use, but it's sort of obvious, so I'm going to say it. What happens if z and its complex conjugate are the same number? What would that tell you?
It's on the axis, or it's on the...
It'd have to be on the real line, right? Right? It would mean that when you reflect it across the real line, nothing happens, right? So it must be on the real line to begin with, right? Okay. So this will happen if and only if z is a real number. Okay. And then the last thing, let's say that z is x plus iy, then zz bar is going to be x plus iy times x minus iy, right? And so you see what's going to happen when you get an x squared, you get an xiy, you get a minus xiy, and you get a minus I squared y squared, right? But I squared, is -1, right? And so you get x squared plus y squared. Okay, right. So that's the last thing I want to say about the simple properties. At this point, we introduce a definition. We define the modulus of z, which is the same thing as it's written with the absolute values. It basically is the absolute value as the square root of z times its complex conjugate. Okay, so that's just the square root of x squared plus y squared, right? The square root of x squared plus y squared. So this is, kind of exactly the same thing as thinking of this as a real vector and taking its norm. Right? Okay, like if we were in a real plane and you had x, y, well, the magnitude of xy is going to be x squared plus y squared square rooted, right? And so we're just doing something similar for complex numbers. Okay. Okay. Everybody all right with that? Okay. Okay. So normally when I do this, I sort of start from nowhere. And then we create the complex numbers for fun. But right now I'm just going to assume that people know what complex numbers are, and we'll go from there. Okay, so everybody all right? Right? Complex numbers, real part of the complex number, imaginary part of the complex number, the complex conjugate, when you reflect the guy across the real axis. There's some properties of the complex conjugate. Probably the most important of which is going to be this one for us, that you can conjugate and then multiply, or you can multiply and then conjugate, right? Conjugate. You can take them in different orders. Right? And then this thing called the modulus. Okay. So that's the just the basics. Okay. And now we're going to say, what does it mean to be differentiable? Okay, so we're going to define differentiability just like we would for real functions. Okay, so let f from E to C, where E is some open set in C, be a function. Okay, so we have some function going from the complex plane to the complex plane, right? It's a complex function. Okay. Some function going from complex plane to the complex plane. Okay, and we have some point in the domain. We have some point in the domain, and we say, sort of naively, if the limit f of z minus f of z naught over z minus z naught as z approaches z naught exists, we call that limit f prime of z naught. We call that limit f prime of z naught and say that f is differentiable at z naught. So you basically use exactly the same definition. The thing is that this is approaching in C, right? As Z approaches Z naught in the complex domain, rather than in the real. Okay. Okay. Just so that we don't get confused, I'm going to call this thing complex differentiable. Okay, complex differentiable, to distinguish it from our previous notion of differentiability. So complex differentiable. Okay. Remark that we could also define it as the limit of f of z naught plus h minus f of z naught over h as h approaches 0, where h is a complex number. Okay, we can also define it that way. Okay, another remark. In some books, you'll see this term complex differentiable. In other terms that are used are holomorphic or analytic. So holomorphic is probably the more popular of these terms. Okay, so yeah, if I say holomorphic, what I mean is complex differentiable. Okay. Okay, everybody all right? All we're doing is saying, let's define a notion of differentiability for complex functions. Okay. Okay, you got a function on the complex plane going from C to C. Right? Takes in complex numbers, gives back complex numbers, and we want to define some sort of differentiability. So you say, okay, we're going to define it basically like we do for real numbers. Okay. Let me give you an example. The function f of z equals the modulus squared. F of z equals the modulus squared. Okay. So remember, the modulus squared is the same thing as z times z bar, right? Z times the complex conjugate. Okay. Now, as a real function, zz bar is just x squared plus y squared, right? Zz bar, this would be sort of like saying f of xy equals x squared plus y squared. Okay. Now this function, if we think about our old definition of differentiability, it is differentiable, right? This guy is, which is a real differentiable function, right? Because it has continuous partials, right? All partials exist, and they're continuous, right? It has continuous partials of every order, right? That's more than enough to guarantee that it's a differentiable function. Okay, so this function, if we think about it as a real valued function, it's differentiable. Okay, but what about thinking about it as a complex differentiable function? Okay, so where could it be? Where could f be complex differentiable? Okay. It turns out that it cannot be differentiable anywhere except maybe as 0. Okay, it's non-differentiable in the whole plane except for at the point 0. And let me show you why that happens. Okay, so at most, it can be differentiable at 0. Why? Why? So let's look. Yeah, so it's a lot harder to be complex differentiable. That's what you should get out of this. This function is real differentiable, but it actually is not complex differentiable basically everywhere. So why? Let's consider f prime of z. Okay. Let's consider f prime of z. Well, f prime of z, that should be the limit of f of z plus something minus f of z over that something, right? As that something goes to 0. Right? That's what we said the definition was. Okay. Well, our function was modulus squared. So that's the limit of the modulus squared. Well, modulus squared is going to be z plus zeta times z bar plus zeta bar. Right? You get the thing times its modulus. I'm sorry, thing times its conjugate, excuse me. Right? Thing times its conjugate. And then we subtract off z times its conjugate. Right? And we divide by zeta. Is everybody all right? Those of you who have been here since the beginning. Those of you who came in late may be kind of confused, but those of you who have been here since the beginning, everybody all right? If you came in late, don't worry, you can watch the video and it'll become clear. Or maybe it's clear already, I hope. Okay, right? So our function is modulus squared, right? Right? Modulus squared, which I said is this. Which we said is the same thing as z times the conjugate. So f of z plus zeta is z plus zeta times the conjugate of z plus zeta. Right? F of z is z times its conjugate. Right? And divide by zeta. Okay. Okay, we're just plugging in. Okay, so then we multiply, right? We get right, we get z bar minus zeta z bar plus z zeta bar minus zeta z bar over zeta. These guys cancel off, right? And we end up with the limit as zeta goes to 0 of negative z bar. Wait, what am I doing? This should be a plus, right? This should be a plus. Why did I put in plus? Why did I put in a minus? And I'm missing something. What am I doing? Okay. Plus zeta bar minus z bar. Okay. Right? So we just, multiply. We just multiply this out, which we should be able to do. Okay, so we end up with z bar minus z zeta bar over zeta plus zeta bar. Right? Z bar plus z zeta bar over zeta. Right? Okay, so nothing amazing. Okay. Okay. Right. So we're looking at the limit as zeta goes to 0 of z bar plus zeta bar plus z zeta bar over zeta. Okay. Right. Okay. So now think. If we let zeta go to 0 along the real axis, if we let zeta go to 0 along the real axis, well, then zeta would be a real number, right? Zeta would be a real number, and that real number would go to 0, right? That real number would go to 0, and since it's a real number, this would be zeta bar over zeta would just be 1, right? Because zeta bar would be equal to zeta, right? Along the real line, the conjugate is the same thing as the number, right? So we would get z bar plus z. Right? Those of you who came in late, if you have a complex number zeta, if you have a complex number z, then z bar is a minus bi. So if this guy is a plus bi, z bar is a minus bi. It's the reflection across the real axis. Okay, so if we let zeta go to 0 along the real axis, we get this. If we let zeta go to 0 along the imaginary axis, we would get what? Well, along the imaginary axis, zeta bar is what? If you have an imaginary number zeta, and you take zeta bar, well, that's the reflection of it, right? This is zeta bar, and you see what that is? That's negative zeta, right? If this guy is bi, this guy is negative bi, right? So we would have negative zeta over zeta. Well, that's -1, right? This thing would go to 0. We would get z bar minus zeta. Right? Right? We get z bar minus zeta. Okay. So for the derivative to exist, this thing has to agree along no matter what path we take to 0, right? And so that tells us that this had better be equal to this, right? Right? So for the derivative to exist, for f prime z to exist, it must be that z bar plus zeta equals z bar minus zeta, right? So that means that z and negative z must be the same guy, and that forces z to be 0. Right? The only place we could possibly be differentiable is at 0. Anywhere else, we're going to end up with different numbers. If we go, right, our limit is not going to exist. Anywhere else, our limit fails to exist. Okay. Louisa. Yeah.
Could you just
Sure, yeah.
explain like
Absolutely.
the along the real axis thing again?
Yeah.
Like how we get that result.
So we're taking this limit thing here, right? Okay. We're taking this limit, the limit of this thing as zeta goes to 0. Zeta is going to 0 in the complex plane. So that is, we can let zeta go to 0 however we feel like. And those have all better be the same thing. Okay. So let's suppose we take zeta going to 0 like this on the real axis. In that case, we get this number. If we let zeta go to 0 like this, we get this number, right? But those should be the same thing.
Yeah.
And so the only place we have a hope of being differentiable is when negative z equals z. Okay. Yeah.
How can you differentiate something at 0 when or how can you differentiate if the function is just 0? If z equals 0, that means the function is 0, right? At 0.
No. I mean, this function is 0 at 0. That's true.
So what would be an example of a function you could differentiate in the complex plane at 0?
I mean, we don't have any complex functions right now to begin with, but
Like we as in like the world, or like we
No.
as class?
this class.
Oh,
this
okay.
class. So, right, we actually don't have any complex valued functions. But if you want a complex valued function, I mean, as this is sort of a dumb one, but you could say f of z equals z. That's a complex valued function. Right?
Yeah.
Right? And you could differentiate it at 0, right? Right. But anyway, maybe a more sophisticated complex valued function would be e to the z. Okay. But what is e to the z? What is e to the z? You actually have to define it using power series. So you say, well, look, e to the x, I know, is summation x to the n over n factorial from n equals 0 to infinity. And you extend that from the real line to the complex plane by allowing the variable to be complex rather than real. Okay. And so you have this power series definition of e to the z, okay, which you can differentiate because of certain properties of power series. Okay. But anyway, yeah, so let's not get too far off track because I want to get to a particular goal, and I'm not even sure if we'll make it. Okay. 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 So, so the moral at this point is that being complex differentiable is more restrictive than being real differentiable. Okay. Okay. So, yeah, being complex differentiable is somehow harder than being real differentiable. Okay. And that moral is sort of epitomized in something called Cauchy-Riemann equations. Cauchy-Riemann equations. Okay, so we've got 20 minutes. I think we can do it. So once we get the Cauchy-Riemann equations, then we'll be able to get to our last goal of using Green's theorem to prove Cauchy's formula. But so suppose that here's the Cauchy-Riemann equations. So suppose that f of z, where z is x plus iy, can be written as u plus iv. Okay, so this is the real part of your function, this is this v guy is your imaginary part of your function. Okay, so suppose you had some function and it looks like, I don't know, like cosine of xy plus I sine of xy. Okay, so you've got some real part of your function, you've got some imaginary part of your function. Okay. 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 Suppose your function looks like that. If f is differentiable at some point z naught being x naught plus I y naught, then in fact the partial of u with respect to x must equal the partial of v with respect to y. The partial of u with respect to y must be the partial of v with respect to x. Okay. So this is the restrictiveness. This is the restrictiveness. Okay. That the partial, that if your function is differentiable, then there has to be some sort of relation between the partial derivatives of u and v. Okay. That doesn't happen for real valued functions. But if you're complex differentiable, then you have to satisfy a set of differential equations. Your real part and imaginary part have to satisfy these differential equations. Okay, and these are called the Cauchy-Riemann equations. Okay, so it's something much more strict, much more constraining than being real differentiable. Okay, so I don't know if we have time to do it. Let's try. So the proof okay, I'm not going to do the proof. I'm not going to do the proof because I think we'll run out of time if we do it. Okay, so but the proof is basically just again you compare the values of the limit as zeta goes to 0 along the real and imaginary axes. Okay, it's basically the exact same argument that we just did, but you do it for this function. Okay, and so you'd say, okay, I'll sort of sketch it out. Let me sketch it out. F prime z naught is going to be the limit of f of z naught plus zeta minus f of z naught over zeta as zeta goes to 0. And you do it in two ways. So you let zeta go to 0 along the real axis. So you let zeta go to 0 along the real axis. Well, that's going to be the limit as zeta goes to 0 of u of x naught plus let me just call it h. Okay, I'm going to call it h because you're comfortable with thinking of h as a real number. Okay, so u of x naught plus h comma y naught plus iv x naught plus h comma y naught minus u of x naught y naught minus iv of x naught y naught over h. Right? So that's what happens if we let h go to h be some real number, right? You get u of blah, 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 and you see what's going to happen, right? You're going to get this minus this over h. Well, what is that? As h goes to 0, you're taking the partial, right? You're taking the first partial, right? You're taking ux at x naught, y naught, and you're adding on iv's first partial at x naught, y naught. Right? You get ux x naught, y naught plus ivx x naught, y naught, right? Because you're just differentiating in the first variable, right? Okay. If you do it along the other axis, letting zeta go to 0 along the imaginary axis, you get, you work it out, and it turns out to be v sub y x naught y naught minus I u sub y x naught y naught. Okay, and so to be differentiable, so for the limit to exist, we need the real part to be this real part and the imaginary part to be this imaginary part. We need these things to be equal, right? Just like before, right? We needed z minus z bar to be equal. I'm sorry, z bar minus z to be equal to z bar plus z, right? So we need these things to be equal, and that tells us that u sub x must be vy, and that v sub x must be negative uy, right? Which is what we said before. Okay, so being complex differentiable sort of forces this system of differential equations to be satisfied by your real and imaginary parts. Okay, this is really important. Okay, now we can get to our goal, which is to show the Cauchy's theorem. Okay. So here we go, Cauchy's theorem. As a consequence of Green's theorem, which is not the right way to do it. If you take a complex analysis class, you're not going to do it this way. But it's kind of a cool, if slightly cheating way of getting the formula. Okay. Although at Mudd, at Harvey Mudd, they actually do it this way because they don't want to take the time to build up the theory. But that's okay. That's okay. They are more interested in the applications and calculations. So that's fine. Yeah, and that may be the only difference between those two courses. Okay. Okay, so here it is. Here's the theorem. If f is holomorphic inside, if f is holomorphic inside and on the simple closed curve and I should say probably smooth, although you don't exactly need smooth. Simple smooth closed curve gamma, then the integral over that curve is 0. Then the integral over that curve is 0. So if you are a differentiable function, then when you get integrated over a smooth, over a curve, over a closed curve, your integral is 0. Okay, just some notation. Let's say f of z is, again, u of z plus IV of Z, right? The real and imaginary parts. Let Z of t be x of t plus Iy of t, where t goes from 0 to 1, be a parametrization of gamma. So this is like our R of t that we've had before. I'm just going to call it Z of t now. Okay, so your parametrization, you have some curve, right? It's parameterized by Z, going from 0 to 1. Okay, and we define the integral. We haven't defined what this is, so you should be like, what is that? We said it's equal to 0, but we didn't tell you what it is. So let's define what that is. That's defined as the integral from 0 to 1 of f of zt z prime t. Z prime t. Okay, what you would expect. Right, which maybe it's cleaner to expand it out and call it u of c of t plus iv of c of t times x prime t plus y prime t dt. I'm just expanding it out, right? I expanded f, like this is your f. This is f of c of t, and then this is z prime t. Okay, so that's the end of the notation, and now let's prove. Now let's prove the theorem. Okay, now let's prove the theorem. We've got 6 minutes. Okay, so the integral of f over gamma is going to be this thing. Is this thing above, right? Is this? Maybe I'll just put a equal sign going this way. Equals this thing above, right? Which I can also write as u plus iv dx plus I dy, using the notation that we had earlier in the term, right? You remember this, like integrating against dx, integrating against dy notation. Anyway, you can just imagine this means this, right? This means this. Okay. So this is the same thing as the integral of u dx minus v dy over gamma plus I times the integral over gamma of u dy plus v dx. Right? I'm just multiplying out. Right? Okay. And now we use Green's theorem. Right? Now use Green's theorem. Use Green's theorem. Right? Green's theorem says that the integral of p dx plus q dy equals dq dx minus dp dy dx dy over the interior. Right? Okay, so we've got this integral u dx minus v dy. We've got this integral u dy plus v dx. right? So we just let P be U, let Q be negative V, right? Right? And so, right, what do you get? You get, for this first part, we use this, and we use Green's theorem. We get the double integral of dq dx, right? So negative dx minus dp dy, right? dA over the interior. Right? That's what Green's theorem says, right? And then we use Green's theorem here, where P is V and Q is U, right? So this says that you get plus I times the double integral of dq dx minus dp dy, dA over the interior. Wait, I've got something wrong. Right, this should be dp dy. Right. Right? Okay. But Cauchy-Riemann equations say that ux is Vy. Right? Do you remember our Cauchy-Riemann equations said that ux is Vy and that uy is negative Vx. The Cauchy-Riemann equations say that this is 0 and this is 0. Right? And so you get 0. Okay. Okay, so if you have a complex differentiable function and you integrate it over a closed curve, then you get 0. And this is Cauchy's formula, Cauchy's theorem, which is kind of like the fundamental building block of one single variable complex analysis, if you ever take a course in complex analysis, which I recommend. It's a cool, because everything is so constrained, the behavior, you get all sorts of wonderful results, like the ones that I mentioned last time. And you can get it using Green's theorem. Okay, that's it. Goodbye.
Wow.